In the previous segment, we introduced the idea of angular acceleration. Recall that angular acceleration is the word we use to describe the rate of increase of the rate of rotation, right? So if the rate of rotation of something is increasing or decreasing, then that object has an angular acceleration. What causes angular accelerations? Well, just like regular accelerations are caused by forces, right? Newton's second law is a cause and effect relationship. It says that acceleration is the effect, force is the cause. Well, if angular acceleration is the effect, what was the cause? Angular force? Sure. I'll give you a better name for it in just a second. Let's start off with a clicker question. Here we see a top view of a door. So we're looking down on this door. You can see the hinge is here. And y'all have had some experience opening doors before. I don't think this is a question that should require a physics class. Which force is going to be most effective at opening this door? Notice we've got F1 here, F2 here right along the door, F3 at some angle, and F4 kind of over here closer to the hinge. Hinge is here. Presumably my door handle is over here. What do you think about it? Pause the video. I'll see you on the other side. If you're not sure, go try it. Go open a door. Notice where you naturally push. You push like this. You push like F1. Right? Why do you push like F1? Well, it's the easiest way to open the door. In order to open the door, we need to give the door some angular acceleration, right? It is stopped now. We need it to be moving. So we need to give it some angular acceleration. So we need the result to be angular acceleration. That means we need to apply some of this angular force. We have a better word for it. A force that's directed in a circular fashion is called a torque. A torque is a push or a pull that's applied in a rotational sense. Mostly we've had experiences with torque. Maybe you never called it a torque, but you've probably used it. I'm going to give you this mathematical definition of a torque. Here's a mathematical definition of a torque. Let's come back to that. Here's a everyday definition of a torque. A torque is the thing you need to make a bolt go in. Okay, let's grab a bolt and see what we need to make it go in. Okay, so a torque is the thing you need to make a bolt go in. Here I've got myself a board on a box, and I have a bolt here. Behold, a lag bolt. I started it here before class. I want to get it farther in. Let me try. I can't. I absolutely cannot turn this. I promise I'm trying really hard. I cannot turn this thing. Now I'm squeezing with my fingers, and I'm applying a rotational kind of a force. So I'm creating a torque. Well, what do I need to create more torque? A socket? Sure. There we go. I just put a socket on there. Now can I turn it? I still can't turn it. So give me a little bit more leverage. What I really need is a socket with a ratchet. Okay, so now I've got a socket with a ratchet on there. I need to get this bolt to go in. How am I going to push? Do I push like this? I don't know. Let's see. Is the bolt going in? No, you do not push like this in order to get the bolt to go in. What do? You have to rotate this. So I don't push like this. I don't pull like this. I push like this, right? From a top view, what I'm doing, right, is I am applying a force like this. I'm applying a force that is perpendicular to the wrench. And this is not the easiest bolt to go in. I did pre-drill my hole, so I can do it fairly effectively, but I'm pushing pretty good. What if I push here? What if I push here instead? Let me see. I seriously cannot make it go, okay? So I'm pushing here. I cannot make it go in. But if I push out here, I can, right? If I push like this, pushing in that direction, nothing. Pulling like this, nothing, right? So what do I need to create a torque? What do I need to create a torque? I need a force, certainly. That force has to be at a distance from the pivot, right? I can't apply my force here. I have to apply it over here. So there's some pivot, some point that it's pivoting around. I need to apply a force, but not at that pivot point. The force has to be separated from the pivot point. And there needs to be some sort of an angle between what I call the lever arm and the force. I can apply force like this, where that angle right there is 90 degrees. That creates a torque. The same force applied like this does not create a torque. Okay, so that's torque as defined as the thing you need to make a bolt go in. Let's see how the math that I'm going to show agrees with that definition. So back to our mathy definition, a torque is a radius, which we're calling the distance from the pivot point to where the force is applied. So we can't apply the force right at the pivot point. If we did, R would be 0, and so would torque. So we have to apply some force at a distance from the pivot point, and the angle between R and F cannot be 0. In other words, I need to be applying my force at some angle to that pivot arm, to that lever arm. Okay. What else can we say? Push or pull, that's a force. A push or a pull that's applied in a rotational sense, that's what a torque is. Units, newtons times meters. If you are working for an engineering firm in the United States, it would be foot-pounds, right? So foot-pounds is the standard in the United States. Okay, so this is our basic equation. Again, torque is the thing that you need to make a bolt go in. We can visualize this in a couple of different ways, right? So we could visualize this as being the force and the sine theta, kind of grouping them together, right? So again, our definition of torque is RF sine theta. In our minds, we could group that F and the sine theta together. In which case, F sine theta, what does that do? Well, here is theta, right? Theta is always the angle between R and F. Right? So here's theta. Notice that F sine theta picks out this perpendicular component. So, in other words, we could have the perpendicular component of the force in all of the radius. So we can write this as R times the perpendicular component of F. Notice this is not a new definition, right? It's not a new definition. It's not even a new equation. It's just a way of grouping F sine theta in our brain. Now, there's no reason at all why we couldn't group the sine theta with the R. And then we'll get a different interpretation where we group the sine theta and the R together, and now we interpret torque as the perpendicular distance to the force. Well, the force is here at one point. And so we need to introduce this idea of the line of action. And this is an idea that will be useful in this section and the next. The idea of line of action. This line of action is this line that extends through the point where the force is applied, and it's along the line of the force. So this is the line of action. And so we can interpret this R sine theta as the perpendicular distance from the pivot to the line of action. We call that the moment arm or the effective lever arm. In other words, all of this radius doesn't count towards increasing our lever arm if the force is not perpendicular to that. It's only the perpendicular distance to the line of action. Again, not a new definition, not a new equation even, just a new way of organizing this same equation in our brain. If we group the R and the sine theta together, we can call that the moment arm. Now we're going to use the same sign convention that we established in the last section, where positive is counterclockwise, negative is clockwise. So in this case, here's six forces, all applied at the same point, all creating 6 different torques. Well, I guess in this case, these two both create 0 torque. They're not doing anything to make this bolt go in. And torque is the thing you need to make a bolt go in or out. This is the maximum positive torque. Why is it positive? Because it's trying to rotate the wrench in a counterclockwise direction. This is something we have to be a little bit careful. The same force can create either a clockwise or a counterclockwise torque. So for example, in this case, my force applied here is creating a clockwise torque. That clockwise torque then would be negative. Why is it clockwise? Because I'm applying this force here and it makes this thing go in a clockwise direction. Is that clockwise? Yes, it is. Okay. So that's clockwise, right? And what did I do? I applied that force upward. Now, what if I apply an upward force over here? Is that still is that still a negative torque? No. An upward force over here, that's trying to rotate it counterclockwise, that is a positive torque, okay? So the same force over here creates a different torque than it would if it was over here, right? So we have to be a little bit careful. The sign of the torque is determined by what direction it's trying to rotate the object, not necessarily just the direction of the force. Here we see a positive torque and a negative torque, but they're not quite as large in magnitude as this positive and this negative. Let's do an example. Revolutionaries attempt to pull down the statue of the great leader by pulling on a rope tied to the top of his head. The statue is 17 meters tall, and they pull with a force of 4,200 newtons at an angle of 65 degrees to the horizontal. And then the questions here are, what is the torque? And if they are standing to the right of the statue, is the torque positive or is it negative? Well, let's go ahead and draw our picture with the revolutionaries standing to the right of the great leader. It might not be that great. Okay, here we go. Great leader. Here's my revolutionaries. Okay. They are standing to the right. They have attached a rope to this guy's head. They are pulling on it like that. They say it is 17 meters tall. And they are applying a force at an angle of 65 degrees. And F equals 4,200 newtons. Okay, so I think that's all of our information. Really, we can just kind of crank through the equation here. Well, we need to be a little bit careful. Let's identify our pivot point, right? So torques are only defined with respect to some pivot point, right? Remember in that equation, we've got RF sine theta. What is R? R is not the radius of whatever round thing is in our problem. R is the distance from the pivot point to where the force is applied. That means that we have to figure out what our pivot point is. Well, if this thing is going to rotate, isn't it going to pivot about this point right here? I think it will, right? And so that tells us that R is right here. Okay, so this phi right here, we have to be careful with that. That's the phi is not necessarily just whatever angle I gave you in the problem, right? Phi is the angle between R and F. So there's R, there's F. That means we need to use this angle right here, which is 25 degrees, and not the 65 degrees. Again, it's because of the definition here. This is phi, it's the angle between R and F. So it's really important that you draw your picture, you identify R, you identify F. Phi is the angle between those two. Now we can just crank through. R is 17 meters. F, 4,200 newtons. Sine of 25 degrees. And we can just run our calculator. We get 30,175. Units, newtons, meters, a couple extra sig figs in there. As you know, that's not my main focus. Okay, there we go. Newtons times meters, that's our unit. Is this clockwise or is it counterclockwise? Well, here's the statue, and they're trying to pull it here, right? Even if they don't topple it, they're trying to pull it this way. So they're trying to pull it in a clockwise sense, and so it is a negative torque by our standard coordinate system. Okay, not too bad. If we had multiple torques, well, then we would just add or subtract them, much like we have with forces. Right, so maybe we put there's the counter revolutionaries. They're over here and they attach a rope. What do we do? Well, we just calculate their torque, and that's in the positive direction. We calculate their torque, that's in the negative direction, and we find the sum. Okay, not too bad.